groups. We were going to go to Utah Lake a few weeks ago and go paddleboarding and kayaking, but unfortunately we were not able to go, and that's because of harmful algal blooms. And that's what we're going to do our presentation on. That's what our research is on. And we're going to talk about why these harmful algal blooms happen, why they're a problem, and what is causing them. And I'm Ethan Rumbaugh.
And I'm Josh Leone, and we worked with Dr. Wang on this research. So this is the outline to the presentation. We're going to start off by introducing some of the main topics, and then move into the methods, talk about our results, and discuss our conclusions. So to start off, I want to talk about Utah Lake and how it's a major feature of Utah County. And as you can see by the purple outline on that little map, the Utah Lake watershed takes up a majority of Utah County and moves into several other counties. And on the map to the right, you can see all of these rivers, which are all inlets, except for Jordan River, which is an outlet river, the only one for Utah Lake. And as you all know, Utah Lake gets algal blooms every summer, and this is due to an excessive amount of nutrients in the water.
And what is a nutrient? So nutrients are good. They are essential to life to thrive and grow. And we especially look at phosphorus and nitrogen. They're essential elements for aquatic life and Utah Lake to grow. They're a natural part of the ecosystem. The issue is when there are too many nutrients in the ecosystem, and that's from overloading nutrients from human activity. This leads to nutrient pollution, and it leads to excessive algae growth. And the reason that this excessive algae growth is bad is because when the algae decomposes, it releases toxins, and these toxins can make people sick. It can harm wildlife, and also the decomposition of the harmful algal bloom depletes the oxygen in the water, and this can cause fish to die. It suffocates them. And this is not good because it hurts tourism, affects our recreation. We're not able to go out on the lake, and it reduces our property values as well.
Okay, and this map shows some of the sources of phosphorus and nitrogen. And some of these sources include atmospheric deposition, like rain and dust, fertilizer from these irrigated fields shown in green, storm runoff, groundwater, and animal feedlot leaks. Our research focused on the wastewater treatment plant specifically, and you can see those little yellow dots. Those are the plants we went to, and we also went to rivers and streams, both their up and downstream sites. And this map shows the elevation difference around this area. And as you can see, Utah Lake is at the lowest point, meaning that everything will eventually end up in the lake. So we tested at 18 river and stream sites and the 7 wastewater treatment plants for a 6-week period. And we tested by using the photometer and the YSI, which we will talk about next. So the photometer tested for the concentration of each of these nutrients. We were specifically looking for nitrogen, and we tested for ammonia, nitrite, and the most abundant one, nitrate, to find nitrogen, and we tested for phosphate to find phosphorus. And this instrument is known as the YSI. It measures several water qualities like temperature, pressure, pH, chlorophyll. We're not going to delve deep into this one, but it helped our research, and yeah.
So for results, so the reason we compared, we went to both an upstream and a downstream site for each river is to compare the upstream to the downstream. The upstreams are the ones by the mountains and where there's less human activity, but as the water flows, it goes into cities and by farms, so nutrients can leak into the rivers that way. And that's what we're seeing. You can see the nutrient concentration in milligrams per liter. It's going to be our y-axis, and on the x-axis is our stream sites. In each box there's the upstream and the downstream, And you can see a general pattern of the downstream sites having a higher nutrient levels, which shows that human activity is leaking nutrients into these streams, which goes into Utah Lake. An example of this is at one of our sites, Dry Creek. It was overflowing and flooding into nearby farm fields, which have fertilizer in them. This leaks nutrients into the water. And as you can see, the upstream site had much higher nutrient levels than the downstream site. And these are some of the highest nutrient levels we saw in the rivers and streams.
And this graph shows the average nutrient levels in the wastewater treatment plants. The x-axis shows the different wastewater treatment plants, and the y being the concentration levels. Ammonia is in black. Nitrate was very high in many of the plants. That's in orange. Nitrite's fairly small, and phosphate is in green. And it doesn't look very big, but there is a mandate that was set by the Utah Division of Water Quality that puts it at 1 milligrams per liter, and most of the plants exceeded that, and we'll talk about that next. But there's no standard for total inorganic nitrogen, but there is one for ammonia, and we'll talk about that later as well.
So yeah, as Josh was saying, there is a phosphorus limit set by the Utah Division of Water Quality, and it went into effect on January 1st of last year. As you can see, not doing a great job, but Timpanogos and Salem are reaching that limit, and the other plants, it's not like they're blatantly not following this limit. They have extensions provided to them for various reasons. One can be just it's expensive to do this, and so they need more time. And so yeah, and the other limit set by the Utah Division of Water Quality is for ammonia, and all the sites are doing well on meeting their monthly max average. Spanish Fork, as you can see, is going over their limit. Limits are set in orange line, but they don't have to meet their limit until the end of 2023. The other ones are current, but they are meeting that limit.
So we can see on this graph the ratios of nitrogen over phosphorus for each of the wastewater treatment plants. And this is important because a healthy ecosystem has a 16:1 ratio of nitrogen over phosphorus. And many of the plants here are under. Provo and Orem wastewater treatment plants do a pretty good job, but Payson, Spanish Fork, and Springville go under, which means they have an excess of phosphorus in their system. And this usually leads to more severe harmful algal blooms. And the ones that go over have an excess of nitrogen in their system. So the conclusions that we came up with is that most wastewater treatment plants go over the mandated limit for phosphorus, but some are able to receive extensions. We found that the downstream sites of rivers and streams have higher concentrations of nutrients than the upstream sites. Nearby farms can leak into the streams or rivers, which increases their nutrient load. And we saw that in that one example, and it increased it by a lot. And there is an excessive amount of phosphorus input into the lake, which can lead to more severe harmful algal blooms. So we would like to thank our professor that we worked with, Dr. Wang, and the rest of the professors that worked on this project. It was very interesting to learn about their research. And we would also like to thank the mentors, Serena and Clayton.
And I'd also like to thank the Utah Department of Water Quality for the work they're doing to keep Utah Lake healthy. And then the U.S. Department of Agriculture for giving us our field trip, and the Natural Resource Conservation Service, and then also the National Science Foundation, of course, for funding this awesome project, and the Utah Lake Commission for their podcasts about the lake, and Utah University for supporting us as their students, and then the Utah Division of Natural Resources for the work they do to bring tourism to the lake and so forth.
Any questions?